Module 23, Lecture B, Biclustering Validation. By the end of this lecture, you will be able to apply spectral co-clustering and spectral biclustering to matrix data, interpret row and column cluster labels and checkerboard structures, and evaluate clustering with external, internal, consensus, and stability measures. Biclustering concepts. Biclustering basics. Biclustering finds patterns in matrix data by grouping rows and columns at the same time. Instead of comparing every row across all columns, it looks for subsets where certain rows behave similarly within certain columns. This reveals local patterns, such as shared patient biomarker responses or shopper preferences in specific categories, that traditional clustering might miss. A bicluster is a submatrix whose rows and columns share a coherent pattern. The pattern depends on the application. Values may be consistently high, change together across conditions, or form a dense region in otherwise sparse data. This flexibility makes biclustering useful for finding relationships that appear only in specific contexts. When using biclustering on matrix data, first clarify what the rows, columns, and entries mean, because this determines how the results should be interpreted. For example, a matrix might connect genes with conditions or users with items, with entries showing expression levels, ratings, or purchases. Before methods such as spectral co-clustering are applied, the data is often transformed or normalized so meaningful associations stand out. The goal is to find interpretable patterns that show where important structures are concentrated. Spectral co-clustering. Spectral co-clustering groups the rows and columns of a data matrix at the same time. It treats the matrix as relationships between two kinds of objects, such as documents and terms, and finds paired groups that form dense blocks. These blocks reveal strong associations, like public health documents linked with terms such as vaccination and outbreak. Spectral co-clustering uses linear algebra to find hidden row and column groups in a matrix. It treats the matrix like a network of relationships, then separates it into groups with strong internal connections and weaker outside connections. This is useful for large, sparse, or noisy data because it highlights broad patterns, such as communities of movie viewers with similar preferences, even when ratings are limited. Spectral co-clustering works best when the matrix entries are meaningful, non-negative values, such as counts or ratings. Careful preprocessing is important, so rows or columns with large totals do not dominate the results. After assigning row and column labels, reorder the matrix to reveal coherent blocks. Then, interpret those blocks in context, such as gene activity patterns or user communities. Python code, spectral co-clustering. This example creates a small checkerboard matrix and uses spectral co-clustering to find connected groups of rows and columns. When the matrix is reordered, the heat map should show clear block patterns. We import key Python libraries for numerical analysis, visualization, and machine learning. NumPy supports efficient array operations, Matplotlib creates plots and charts, and Scikit-Learn provides tools for data analysis. We also import the spectral co-clustering class, which groups both rows and columns of a matrix to help reveal hidden patterns. A fixed seed of 42 is used with NumPy's random number generator, so the synthetic matrix is created the same way every time. This makes the random values repeatable, which supports reliable testing and comparison across runs. We create synthetic checkerboard data by first defining a small base matrix with strong links between 3 row groups and 3 column groups. Then, we assign true row labels by repeating the group numbers 0 through 2, so that each group covers 10 rows. We do the same for columns, with each of the 3 groups covering 8 columns. These labels define the intended block structure used to test spectral co-clustering. We build the synthetic data matrix from base blocks chosen according to predefined true row and column labels. Then, we add normally distributed noise, centered at 0, with a standard deviation of 0.8, to mimic real-world variation. Finally, values are clipped at 0, so the data remains non-negative for later analysis. The code applies spectral co-clustering to group the rows and columns of a matrix at the same time. It creates a model with 3 clusters, sets a random state for reproducible results, and fits the model to the matrix to find linked row and column groups. To reveal structure in the data, we sort the rows and columns using the labels learned by the spectral co-clustering model. This places similar rows and similar columns next to each other. Reordering the original matrix this way makes hidden block patterns easier to see. The output first reports the Scikit-Learn version to support compatibility and reproducibility, then shows the matrix shape to confirm the data dimensions. It also summarizes the learned row and column clusters by counting how many items fall into each group, making the spectral co-clustering results easier to interpret. This visualization creates a heat map of the reordered matrix using Matplotlib. The image shows connection strengths with the Viridis color map, while the title and axis labels explain that rows and columns have been sorted by the clusters learned through spectral co-clustering. A color bar provides the scale for association strength, and the plot is then displayed. This script shows spectral co-clustering on a noisy synthetic checkerboard matrix with 3 row and column groups. It uses Scikit-Learn to learn the clusters, then reorders the rows and columns so related entries appear together. The output reports basic details such as the Scikit-Learn version, matrix size, and cluster sizes, and a heat map confirms the checkerboard block structure. Spectral biclustering. Spectral biclustering clusters rows and columns of a data matrix at the same time to find checkerboard-like block patterns. It identifies groups of rows that behave similarly across specific groups of columns, rather than clustering only one dimension. By using spectral information such as singular vectors or eigenvectors, it maps the data into a lower dimensional space, where these shared row-column structures are easier to detect. Spectral biclustering reorganizes a matrix so related rows and columns form clear blocks, often appearing like a checkerboard of different values. It is useful for finding linked groups, such as genes and conditions, customers and products, or documents and shared vocabulary. The method normalizes the data, extracts the main structural patterns, and clusters them to reveal relationships between row and column groups. Spectral biclustering works best when the matrix values are meaningful, non-negative measures, such as frequencies or intensities that show row and column associations. Careful pre-processing is important because differences in scale, sparsity, or variance can cause some features to dominate the results. After fitting the model, reorder the matrix to see whether the discovered blocks reveal useful patterns, such as patient responses or customer preferences. Python code. Spectral biclustering. This example shows how spectral biclustering can find checkerboard patterns in matrix data by grouping rows and columns together. After reordering the matrix, the heat map should reveal a clearer block structure. We import NumPy for efficient array handling and numerical work, and Matplotlib's plotting tools for creating visualizations. We also import Scikit-Learn for machine learning support, including the spectral biclustering class, which finds patterns by clustering both rows and columns of a data matrix. We create a NumPy random number generator with a seed of 42 so the results are reproducible. This means the same random numbers are generated each time the code runs, which helps with debugging and lets others repeat the experiment under the same conditions. A block means matrix is defined with NumPy to set the average association strength for each block. It is a 3x3 array, where each value controls the typical strength of one block in the synthetic data. This helps create distinct groups in the larger matrix used for biclustering. A base matrix is created by repeating the block means across rows and columns, forming larger groups with similar values. Random normal noise with mean 0 and standard deviation 0.6 is then added to make the data more realistic. Finally, the values are clipped at 0, so the resulting association strengths are never negative. Before fitting the model, the code verifies that the data matrix has 30 rows and 24 columns. If the dimensions are different, it raises an error to signal the mismatch. This check helps ensure the data is properly structured and prevents problems during model fitting. Spectral biclustering is used to find a checkerboard-like block structure in a data matrix. The model is set to form 3 row groups and 3 column groups, with a fixed random state for reproducible results. After fitting the model to the matrix, it identifies the row and column clusters that best reveal the underlying pattern. To visualize the spectral biclustering results, the data matrix is reordered using the model's learned row and column labels. Rows with similar labels are grouped together, and the same is done for columns. This rearrangement makes the checkerboard structure found by the model easier to see. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then shows the first 12 row and column cluster labels from the spectral biclustering model. These labels identify how rows and columns were grouped, helping confirm that the model output matches the clustering pattern shown in the heatmap. A heatmap is created by setting up a Matplotlib figure and displaying the reordered matrix with the imshow function using the Viridis color map. The plot is titled to show it represents a spectral biclustering reordered matrix, with axis labels indicating that rows and columns are sorted by their learned clusters. A color bar provides the scale for association strength, and the final display helps reveal the checkerboard pattern found by spectral biclustering. This script uses spectral biclustering to find checkerboard patterns in a synthetic matrix. It creates a reproducible noisy matrix with distinct block means, checks its dimensions, then clusters both rows and columns. After reordering the matrix by these clusters, a heat map shows clearer block structure, confirming that the method has identified meaningful row and column groupings. The script also reports the Scikit-Learn version and sample cluster labels to help interpret the results. Bicluster outputs. Row-column labels. In biclustering, labels are assigned to both rows and columns to show how a matrix is divided into related groups. This differs from regular clustering, which groups only one set of items. For example, row labels might group similar patients or customers, while column labels might group genes or products with related patterns. These labels help turn the algorithm's output into meaningful, interpretable patterns. In biclustering, a bicluster is the intersection of a row group and a column group, so row labels only become fully meaningful when considered with column labels. In educational data, this can connect groups of students with groups of assessment items to show patterns such as strength in conceptual questions and difficulty with procedural ones. This helps turn a complex data matrix into clearer relationships between observations and features. In biclustering, row and column labels are just arbitrary names assigned to groups, not signs of importance or hierarchy. To interpret them, you must look at the underlying data values, the context, and any relevant outside information. The labels serve as starting points for understanding and explaining the patterns that the biclustering process reveals. Python code. Row-column labels. This example shows how biclustering labels correspond to blocks in a matrix. Row and column labels form checkerboard-like intersections, and the resulting block means make the biclusters easier to interpret. The script imports the main tools needed for the analysis: NumPy and pandas for working with numerical data and data frames, spectral co-clustering from Scikit-Learn for clustering rows and columns together, and Scikit-Learn itself to check version information. Together, these imports prepare the code for data handling and biclustering. We create a small 3x3 matrix with a checkerboard pattern to serve as the basis for a biclustering example. Then we define row and column groupings by repeating group labels, which sets the structure of the data. These groupings map the matrix into a checkerboard layout, making it suitable for demonstrating biclustering. A fixed random seed is used so the added noise is reproducible. The data matrix is built by selecting values from base blocks according to row and column groups, creating a larger repeating structure. Normally distributed noise with mean 0 and standard deviation 0.25 is then added to simulate realistic variation while preserving the main pattern. Spectral co-clustering is used to estimate row and column labels at the same time. A 3-cluster model is fit to the data with a fixed random state for reproducibility. The model groups similar rows and columns to reveal the matrix's underlying checkerboard pattern. To reveal the checkerboard structure found by the clustering model, we sort the row and column labels to define a new order. We then rearrange the original data matrix using that order. This makes the model's underlying pattern easier to see and interpret. Create a 3x3 matrix to store the average value for each block. For every pair of row and column labels, from 0 to 2, select the matching rows and columns in the data, compute the mean at their intersections, and place it in the corresponding matrix position. This produces a compact summary of the checkerboard pattern by capturing the mean for each labeled block. A pandas data frame is used to present the average values of matrix blocks by their row and column labels. The block means are rounded to 2 decimal places for readability, and descriptive row and column labels make the table easy to interpret. This creates a clear summary, linking each label combination to its average matrix value. The code reports the Scikit-Learn version to confirm the working environment, then shows sample row and column cluster labels from the spectral co-clustering model. It also summarizes the mean values for each row and column cluster combination, helping make the bicluster patterns easier to interpret. This script shows how biclustering can uncover a checkerboard pattern in a matrix. It builds a block-structured matrix with added deterministic noise, then uses spectral co-clustering from Scikit-Learn to group similar rows and columns. After sorting the matrix by the estimated labels, the hidden block structure becomes clearer. The output includes the Scikit-Learn version, sample row and column labels, and mean values for each row-column label intersection to summarize the biclusters. Checkerboard patterns. A checkerboard pattern helps summarize biclustering by reordering a matrix so similar rows and columns appear together. This creates rectangular blocks, where each block shows how one row cluster relates to one column cluster. The result highlights meaningful regions with distinctive values, such as specific gene behavior under certain conditions. A checkerboard pattern is interpreted by looking at both how blocks are arranged and what values they contain. Important blocks may show consistently high or low values, or sharp contrasts with nearby blocks. This view helps reveal how particular subgroups relate to specific features, making it more informative than clustering rows or columns alone. A checkerboard pattern can help assess biclustering by revealing clear blocks in a reordered matrix, but real data often contains noise, overlap, or blurred boundaries. Imperfect patterns do not necessarily mean the biclustering is poor, especially in complex settings like healthcare or text analysis, where groups may naturally overlap. The checkerboard should be used as a guide for finding stable, meaningful relationships, not as a requirement for an ideal pattern. Python code, checkerboard patterns. This example creates a small checkerboard matrix, where row and column labels define rectangular biclusters. By reordering the matrix, the hidden block pattern becomes easier to see. The script imports key libraries for numerical work, visualization, and clustering. NumPy handles arrays and calculations. Matplotlib creates the checkerboard display, and Scikit-Learn's spectral co-clustering algorithm groups similar rows and columns in the matrix. The full Scikit-Learn library is also imported, so its version can be checked for compatibility and reproducibility. We create a NumPy random number generator and seed it with 42, so it produces the same random numbers each time the code runs. This makes the example repeatable and reliable for testing or demonstration. A two-dimensional array is used to store the average interaction values between row clusters and column clusters in a checkerboard pattern. Each value represents one block where a row cluster and a column cluster meet. These block means define the distinct patterns in the matrix and support later demonstrations of clustering techniques. To build the matrix, we set the row and column cluster sizes first. There are 3 row clusters with 8 rows each, and 3 column clusters with 6 columns each. This structure prepares the matrix for later shuffling and pattern analysis. A checkerboard matrix is built by combining constant filled blocks with NumPy's block and full functions. Each block size comes from the row and column cluster sizes, and each block value comes from the corresponding entry in the block means array. The result is a structured matrix where constant regions represent interactions between row and column clusters. A noisy dataset is created by adding normally distributed random noise to the true matrix, simulating imperfections in real data. The rows and columns are then randomly shuffled using separate random orderings. The resulting matrix has hidden structure obscured by both noise and disorder, making it suitable as input for clustering. We create a spectral co-clustering model with 3 clusters and a fixed random state for reproducibility. After fitting it to the shuffled matrix, the model estimates row and column groups to reveal the hidden checkerboard structure in the data. To reveal the matrix's block structure, we sort the rows and columns by the cluster labels from the spectral co-clustering model. Reordering the shuffled matrix with these sorted indices places similar rows and columns next to each other, making the hidden pattern easier to see. The code verifies that the reordered matrix has the expected size of 24 by 18. If the dimensions do not match, it raises an error to signal that the transformation failed. This check helps ensure the matrix is valid before it is used for further analysis or visualization. The process first checks the Scikit-Learn version to support compatibility and reproducibility. It then counts how many rows and columns are assigned to each estimated cluster. Using the model's labels, these counts summarize the cluster sizes and show how the data is distributed across the row and column groups. We create a Matplotlib figure and axis to serve as the plotting area, then display the reordered matrix as a heat map using the image display function. The Viridis color map and automatic aspect ratio make the visualization clear and well fitted to the figure. This helps reveal the checkerboard pattern in the reordered matrix. The plot is labeled to show a checkerboard pattern after biclustering, with rows and columns sorted by their estimated clusters. The axis labels explain this ordering, while the color bar shows how colors correspond to matrix values. Finally, the visualization is displayed on the screen. This script creates a noisy checkerboard matrix, then shuffles its rows and columns to hide the block pattern. It uses spectral co-clustering in Scikit-Learn to estimate row and column groups and reorder the matrix so the hidden structure becomes visible again. The result reports the Scikit-Learn version and cluster sizes, then shows a heat map of the reordered data. demonstrating how co-clustering can reveal patterns in complex data. Consensus scores. Consensus scores measure how consistently rows and columns are grouped across repeated biclustering runs. Because results can change with initialization or data variation, a high score suggests the grouping is stable rather than random. In practice, this means the same gene expression patterns or customer product segments are repeatedly found across analyses. Consensus scores help judge how reliable a bicluster is by connecting the score to its row and column labels and the checkerboard pattern they form. A high score means the same rows and columns tend to appear together across repeated solutions, so the group can be interpreted with more confidence. A low score suggests instability, where items shift between groups, so the result should be treated cautiously. In document analysis, this can indicate whether a topic is coherent or whether it reflects mixed themes or weak vocabulary patterns. Consensus scores help compare biclustering results by showing which patterns remain stable when data is resampled or algorithms are rerun. This matters because similar-looking checkerboard patterns may differ in reliability. A high consensus score suggests a bicluster is worth further study, while a low score signals caution. Overall, consensus scores make bicluster interpretation more trustworthy by measuring how consistently patterns appear across repeated analyses. Python code. Consensus scores. This example evaluates consensus across repeated biclustering runs by checking whether pairs are grouped together consistently. Stable row and column labels indicate more reliable patterns and make the results easier to interpret. The code imports the main tools needed for the workflow: NumPy for numerical array operations, Matplotlib for creating plots, and Scikit-Learn's spectral co-clustering algorithm for finding biclusters in data. It also imports Scikit-Learn itself, so the script can check the library version later. To make the synthetic matrix reproducible, we use NumPy's random number generator with the seed set to 42. This ensures the same random values are produced each time, which is important for reliable testing and comparison. To create a checkerboard structure, the data is divided into 3 row groups and 3 column groups. The row indices repeat the group labels 0 through 2 to make 30 rows, while the column indices repeat the same labels to make 24 columns. Together, these groupings organize the data into distinct blocks for each row and column group combination. A 3x3 matrix of block averages defines the checkerboard pattern. By using the row and column group assignments to select from these averages, each block is filled with its corresponding mean value, creating the clean synthetic data matrix. Small random noise is added to the clean matrix to make the data more realistic, while keeping the checkerboard pattern visible. The noise comes from a normal distribution centered at 0, with a standard deviation of 0.8. Afterward, the matrix is shifted by subtracting its minimum value and adding 0.1, ensuring all entries are positive for later use. The code verifies that the data matrix has 30 rows and 24 columns. If the size is wrong, it raises an error to stop the process. This helps ensure the data is valid before later analysis begins. To check whether biclustering labels are stable across repeated runs, we create 2 zero-filled consensus matrices. One records how often pairs of rows are clustered together, and the other does the same for pairs of columns. As runs accumulate, these co-occurrence counts provide a measure of clustering stability. The process runs spectral co-clustering 10 times, using a different random seed for each reproducible run. Each model groups the data matrix into 3 clusters. After each fit, the row and column labels are compared pairwise to count how often items are placed in the same group. These counts show how consistently rows and columns cluster together across runs. The code normalizes row and column pair counts by dividing them by 10, giving consensus scores across 10 biclustering runs. These scores show how consistently rows and columns are grouped together across repeated clustering attempts. To compare consensus within true groups and across different groups, we identify which pairs of rows or columns share the same group label. This creates simple true or false matrices for row pairs and column pairs. These matrices are then used to compute average consensus scores within groups and between groups. To assess clustering reliability, we compare average consensus scores for pairs that should be grouped together with pairs that should be separated. This is done for both rows and columns, measuring how stable the within-group assignments are and how often different groups are incorrectly clustered together. Higher within-group consensus and lower across-group consensus indicate more reliable clustering results. The code first reports the Scikit-Learn version to help confirm compatibility. It then summarizes clustering reliability by comparing consensus within true groups and across different groups for both rows and columns. High within-group consensus and low across-group consensus indicate more stable and accurate clustering results. Create a 6 by 5 inch plotting area, then display the row consensus matrix as a heat map using the image display function. Set the color scale from 0 to 1 so the full range of consensus scores is visible, and use the Viridis color map to make differences easier to interpret. The plot is titled to show that it displays row consensus across repeated biclustering runs. Both axes represent row indices from the data matrix, and the color bar indicates the consensus score scale. Displaying the heat map lets us visually assess how consistently pairs of rows are grouped together across runs. This script tests how stable biclustering is on a synthetic matrix with clear block structure and added noise. It runs spectral co-clustering 10 times with different random seeds, then measures how often each pair of rows or columns is placed in the same group. Strong agreement within the true groups and weak agreement between different groups suggest reliable clustering. The script reports average consensus scores and uses a heat map to show which row pairs are consistently clustered together. Validation metrics. External validation metrics. External validation metrics assess whether biclustering results match known outside information. Because biclustering groups both rows and columns, validation checks whether the discovered row and column subsets correspond to meaningful labels, such as known gene pathways or clinical sample types. The goal is to confirm that the biclusters reflect real-world structure, not just patterns found within the data matrix. External validation in biclustering measures how well discovered biclusters match known labels, without caring about the names assigned to clusters. Measures such as purity, normalized mutual information, and the adjusted RAND index compare membership agreement for rows, columns, or both. A high score means the biclusters align with a chosen external standard, but it does not prove they are the best possible representation of the data. External validation metrics for biclustering should be interpreted carefully, because reference labels may be incomplete, noisy, or not aligned with the patterns being sought. A low score can still indicate a useful new structure that crosses known categories, while a high score may simply reflect rediscovery of existing labels. For this reason, external metrics should be combined with internal checks and expert judgment to assess both statistical quality and practical value. Python code, external validation metrics. This example evaluates biclustering by comparing its results with known labels. External metrics measure how well the predicted groups match trusted categories, with higher agreement indicating better recovery of the reference structure. We import NumPy for efficient numerical work, and Scikit-Learn for machine learning tools. From Scikit-Learn, we use spectral co-clustering to group both rows and columns of a matrix at the same time. We also import adjusted RAND score and normalized mutual information score to compare the clustering results with known labels and assess accuracy. We create a NumPy random number generator with a seed of 42, so the same random values are produced each time the code runs. This makes the results reproducible, which is useful for testing, debugging, and consistently generating the same synthetic data. We define the true row and column labels as benchmark categories for validating the clustering results. The row labels contain 3 groups, with 0, 1, and 2 each repeated 8 times, while the column labels contain the same 3 groups repeated 6 times each. These known labels provide the external standard for comparison. The code defines average values for row and column blocks, then uses the true row and column labels to build a synthetic data matrix from those averages. This gives each block a distinct mean value, creating data with known structure. The result is a controlled setup for testing biclustering methods on patterns that are already understood. To make the synthetic matrix more realistic, we add small random noise to the clean data. The noise comes from a normal distribution with mean 0 and standard deviation 0.6, and it has the same shape as the data matrix. This gives each element a slight random adjustment, simulating real-world imperfections while keeping the data manageable. The code applies spectral co-clustering to find related groups in both the rows and columns of a noisy matrix. It uses 3 clusters and a fixed random state for reproducible results, then fits the model to estimate the row and column groupings together. The code evaluates clustering quality using the adjusted RAND index. It compares the model's predicted row labels with the true row labels, then repeats the comparison for column labels. These scores show how closely the clustering matches trusted labels, while ignoring differences in the names or order of clusters. Normalized mutual information, or NMI, measures how closely 2 sets of labels agree, with a score from 0 to 1. We compute it separately for rows and columns by comparing the true labels with the model's predicted labels. Higher scores show that the model's clustering better matches the known structure. The output first shows the Scikit-Learn version to support compatibility and reproducibility. It then reports clustering quality for both rows and columns using the adjusted RAND index and normalized mutual information. Together, these scores compare the predicted clusters with the known labels and help assess how well the clustering matches the true structure. This script tests how well a spectral co-clustering model recovers known row and column groups in a synthetic, noisy matrix. It compares the predicted clusters with the true labels using the adjusted RAND index and normalized mutual information for both rows and columns. Higher scores mean the model's clustering more closely matches the original block structure, and the output reports these scores along with the Scikit-Learn version. Internal quality scores. Internal quality scores evaluate biclustering results using only the data matrix and the discovered row and column groups, without relying on labels or external references. This is especially useful in exploratory analysis, where the goal is to find unknown patterns. In density biclustering, these scores judge whether selected submatrices are dense, coherent, and distinct from the rest of the data, such as groups of active genes under certain conditions or customers buying related products. Bicluster quality is judged mainly by coherence, separation, and coverage. A good bicluster shows a consistent internal pattern, is clearly distinct from the rest of the matrix, and covers enough data to be useful without becoming too broad. Analysts aim for biclusters that are consistent, sufficiently large, non-redundant, and meaningful in their domain. Internal quality scores for biclustering can favor different kinds of results, such as smaller, more uniform biclusters, or larger, noisier ones with broader coverage. The best score is not simply the highest one, it should match your scientific or business goal. In practice, compare several scores, inspect the resulting biclusters, and check that the patterns make sense in your domain. Use these scores to support judgment, not replace it. Python code, internal quality scores. This script evaluates biclusters without using external labels. It uses internal scores to measure density, coherence, and coverage, helping identify biclusters that clearly stand out from background noise. The script imports key Python tools for data analysis and machine learning. NumPy supports efficient array and numerical operations, while Matplotlib's plotting module is used for visualizations. It also imports Scikit-Learn's spectral co-clustering algorithm to find biclusters by grouping rows and columns together, and loads Scikit-Learn itself, mainly to check its version later. A reproducible random number generator is created with a seed of 42. It is then used to generate a 30 by 24 synthetic data matrix with values drawn from a normal distribution centered at 0 and a standard deviation of 0.4. This matrix provides the base data for the biclustering analysis. We create 3 hidden bicluster patterns by increasing values in selected matrix blocks. The top left block receives the largest boost, the middle block a slightly smaller one, and the bottom right block another strong boost. These changes form 3 dense high-value regions that a clustering algorithm can later detect as distinct biclusters. The code applies spectral co-clustering to find hidden structure in a matrix by grouping similar rows and columns together. It creates a model with 3 clusters, uses a fixed random state for reproducible results, and fits the model to the data to identify the patterns that define those groups. The code validates that the model's row and column labels match the matrix dimensions. Each row and column must have a corresponding label for clustering to be accurate. If either count does not match, it raises an error, helping ensure the biclustering process uses correctly labeled data. To evaluate each bicluster, we collect 3 key statistics: its mean, standard deviation, and size. For every cluster found by the model, we select the matching rows and columns, extract the corresponding block from the matrix, and compute these values. Together, these summaries help assess the internal quality of each bicluster. The code first finds the average value of the whole matrix to use as a baseline. It then compares this with the average value of the clustered blocks. The difference, called density lift, shows how much those blocks stand out from the overall background, with higher values indicating stronger, denser blocks. The coherence score measures how tightly grouped the discovered blocks are by using their average internal variation. Lower variation gives a higher coherence score, meaning the blocks are more consistent. The coverage score measures how much of the matrix is included in the identified biclusters, with higher coverage indicating that more elements are represented. The script reports the Scikit-Learn version to support compatibility and reproducibility, then summarizes biclustering quality with 3 metrics. Density lift shows how much stronger the bicluster values are than the matrix average. Coherence measures how consistent values are within biclusters, and coverage indicates how much of the matrix the biclusters capture. To reveal the matrix's checkerboard pattern, we reorder its rows and columns using the cluster labels found by the spectral co-clustering model. Sorting both dimensions by their assigned clusters creates a rearranged matrix where related rows and columns are grouped together, making the underlying bicluster structure easier to see. A new Matplotlib figure and axis are created to set up the visualization canvas. The reordered matrix is then displayed as an image, with the aspect ratio adjusted automatically to fit the figure. Using the Viridis color map helps distinguish matrix values and makes the checkerboard pattern from spectral co-clustering easier to see. The plot is labeled to show that the matrix has been reordered using spectral co-clustering. Its rows and columns are sorted by the clusters found by the model, and a color bar shows the range of matrix values. Displaying the plot lets us inspect the checkerboard pattern produced by the clustering. This script tests how well spectral co-clustering finds hidden biclusters in a synthetic matrix. It creates a random matrix with 3 added dense blocks, then groups rows and columns to recover those structures. The results are evaluated with internal measures of density, coherence, and coverage, showing how strong, consistent, and extensive the detected biclusters are. Finally, the matrix is reordered and displayed to make the checkerboard bicluster pattern easier to see. Stability selection. Stability selection in biclustering tests whether the same row and column groups reappear when the data or algorithm changes slightly. In density biclustering, this helps distinguish meaningful patterns from random noise. If a bicluster is stable across repeated analyses, the result is more trustworthy and likely reflects a genuine structure in the data. To assess biclustering stability, rerun the method with small changes such as resampling, added noise, or adjusted settings. Then compare whether similar row and column groups reappear. Because biclustering works across both dimensions, the key question is whether the main shared structure remains consistent, even if some elements change. A bicluster is more trustworthy when its core pattern appears repeatedly across runs. Stability selection helps judge whether a biclustering result is reliable, not just whether it scores well. External metrics need known labels, and internal scores can measure fit or compactness, but neither fully shows robustness. If small data or parameter changes produce very different groupings, analysts should be cautious. Patterns that remain consistent across changes are stronger candidates for further analysis and reporting. Python code stability selection. This example evaluates biclustering stability through resampling. If the labels are stable, they should remain consistent across repeated runs, and the reported scores provide a clear summary of reproducibility. We import NumPy for efficient array handling and numerical work, and use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in spectral co-clustering to find biclusters in data, along with the adjusted RAND score to compare clustering results and assess their stability. A fixed random seed is used so the synthetic matrix can be reproduced exactly. The rows and columns are each assigned to 3 repeating groups, creating a structured checkerboard pattern. This setup provides controlled synthetic data for testing the stability of a biclustering model. We define a small matrix of block means to represent the true bicluster structure. These values are expanded across predefined row and column groups to create a larger base matrix with the intended pattern. Random normal noise with mean 0 and standard deviation 0.6 is then added to simulate real data variation, producing the final matrix for biclustering analysis. Before fitting the model, the code verifies that the data matrix has 36 rows and 30 columns. This confirms the data matches the expected structure for biclustering. If the dimensions are wrong, it raises an error and stops the model from using incorrect data. We create a reference spectral co-clustering model with 3 clusters, matching the structure of the synthetic data, and use a fixed random state for reproducible results. After fitting the model to the full data matrix, we extract the row and column group labels. These labels capture the detected bicluster structure and provide a baseline for later stability comparisons. To assess biclustering stability, the process runs 20 trials on slightly noisy versions of the data matrix. In each trial, a spectral co-clustering model with 3 clusters is fit using a different random seed. The resulting row and column labels are compared with the reference labels from the original data using the adjusted RAND score. The collected scores show how consistently the biclusters are recovered under small data perturbations. We summarize clustering stability by calculating the average row and column scores, which shows how consistently clusters are found across runs. We also find the lowest row and column scores to identify the least stable results. Scores closer to 1 indicate more reliable cluster groupings. The code reports the scikit-learn version for reproducibility, then summarizes clustering stability using adjusted rand index scores for rows and columns. It shows both the average stability and the lowest observed stability, rounded to 3 decimal places. Scores close to 1 indicate that the checkerboard clustering pattern is consistently reproduced across data perturbations. This script tests how stable spectral co-clustering is on a noisy synthetic checkerboard dataset. It fits one reference biclustering model, then refits the model several times after small data perturbations. Each new result is compared with the reference using the adjusted rand index for both rows and columns. Mean and minimum scores close to 1 show that the biclustering remains consistent and robust under small amounts of noise. In this lecture, you learned to apply spectral co-clustering and spectral biclustering to matrix data, interpret row and column cluster labels and checkerboard structures, and evaluate clustering with external, internal, consensus, and stability measures. In the next module, Module 24, we will go over matrix decomposition.
Thank you for your attention. See you all in the next lecture.